we're finishing up our angular dispersion problem. So we went through and we found, in the last video, we found that refracted angle for this red beam of light. And I'll come back to this image at the end of the problem. So basically, if you take this dotted line, right, and you move it down a little bit to where this red beam is exiting the prism, you'll see that this is perpendicular to the surface, right? So the angle between this red beam and that line, like if I move this line down here, that's the final refracted angle that we found for the red light, and that was 58.6 degrees. So we're going to do the same thing for the violet light, and then what we're going to see is we take this same line, bring it down here. It's still a normal line, still perpendicular to the surface, and so that the angle that we're going to get for violet is going to be the angle that this beam makes with that dotted line again. And the difference between those two angles is going to be what is referred to as this angular spread here. So we expect violet to have a larger angle of refraction. So the angle this makes with that line minus the angle the red light makes with that line is going to be this angular dispersion, this how the light is spread, how much the light is spread between red and violet. So we go through the same process for violet. Everything is identical with the exception of the index of refraction for violet. So we're looking for the same thing. We're looking for the final refracted angle for the violet light. So the diagram is going to look the same as it did for our red light. The difference is because we've got a higher index of refraction for violet, it's 1.66. Theta 2, my initial refracted angle is going to change. That means the phi 2, the phi 3, and the theta 3, the second incident angle over here, is also going to change. But again, the algebra is the same. We're going to use Snell's law here. We're going to use the property of the interior angles of a triangle. All three of these add up to 180. We're going to find out what phi 2 is once we get theta 2. Find out phi 3, theta 3, use Snell's law again to find theta 4. So hopefully after watching the video you took a minute and you did this for violet already. This is good practice because again the process is the same, just a different index of refraction for violet. Snell's law at the first surface of the prism, we're solving for theta 2, that first refracted angle. Take the inverse sine of both sides, or divide both sides by the index of refraction for violet because we're looking for theta 2. Take the inverse sine of both sides, plug my values in. Same initial incident angle. Remember, it comes in as white light and then it gets dispersed into the different colors. So theta 2 for violet, the first refracted angle for violet is 27.5 degrees. So we take 27.5 degrees complement, we get phi 2, which is 62.5. So this angle phi 2 for violet is now 62.5. This is 60. Phi 3 plus phi 2 plus 60 have to equal 180. So we solve for phi 3 using the same relationship we did here for red. And phi 3 is equal to 57.5 degrees. Once again, we have to take phi 3's complement to find the incident angle on the second surface of the prism. So phi 3 is 57.5. We need this angle because it's measured from the normal line. So we take phi 3's complement. Theta 3, my new incident angle, is 32.5 degrees. Now we're using Snell's law again, but we're going from the prism to the air. So we have to use the index of refraction inside the prism for violet times the sine of the incident angle. My new incident angle is theta 3 is equal to the index of refraction for air because it's exiting the prism times the sine of theta 4. That's what we're looking for, my final refracted angle for violet. Again, algebra is the same, except we're dividing both sides by n sub a. Take the inverse sign of both sides to get theta 4 by itself. Plug in our values. That's 1. I forget to plug that in, sorry, but that's the index of refraction for air. So 1.66 times the sine of theta 3, my new incident angle, and I get 63.1. So we've got a larger refracted angle, higher index of refraction for violet. Violet light is dispersed farther than the red light, so we're just looking for the difference in the final refracted angle. So we're going to take 63.1 degrees and subtract that final refracted angle for red from that, and then we're going to get the angular dispersion. So that's the angle. 4.5 degrees is the angle between the red beam and the violet beam. So this angle right here is 4.5 degrees. Now it's a little exaggerated here so we can see all the colors of the visible spectrum, but it's very, very small angular dispersion, 4.5 degrees. So we do the same process for red as we do for violet. Snell's law twice. Use a little geometry to find the new incident angle. Use Snell's law that second time. Find the final refracted angle for both colors, and then take the difference and we find the dispersion. So we're looking at how light refracts when passing from one medium to another, and we see Snell's law gives us a way to determine the refracted angle, right? So we had a scenario a couple slides ago where a laser beam was incident to a surface, but it was perpendicular to the surface. So the incident angle was 0, sine of 0 is 0. That means the refracted angle had to be 0, right? But then as you change that incident angle, the refracted angle changes with respect to Snell's law. There's a little portion possibly that gets reflected back into the medium. Up to this point, we've been dealing with light that is passing through a medium with a low index of refraction and then entering a medium with a high index of refraction. And then it exits with our prisms, our two prism examples. It exits from a high index of refraction to a low index of refraction. But in both cases, we've just been dealing with the refracted ray. And we're looking for the refracted angle. We use Snell's law and a little bit of geometry to find out what that is. As you increase the incident angle, right? You see every point here, right here, right here, right here. You draw a normal line, and we're increasing the incident angle. So it makes sense that the refracted angle increases due to Snell's law. But then there's a limiting case, right? There's a limiting case where eventually your incident angle is sufficiently large to where your refracted angle is 90 degrees. So that means your beam, in theory, would travel along the edge of this medium. Now we're going from a high index of refraction to a low index of refraction. So think about a beam traveling through like a glass prism and then exiting and then entering into air or water or something like that. But there's a case where the incident angle is sufficiently large that the refracted angle is 90 degrees. Now when you go above that, angle, that max incident angle, all of that light becomes reflected back into the medium. So there's actually no refraction occurring once you get above this angle. We call that angle the critical angle. So the critical angle is the incident angle that you need to project that light for the refracted angle to be 90 degrees. And once you get over that critical angle, we have what's called total internal reflection. So that means there's no refraction, no light enters the second medium, all of it gets reflected inside. And we use this technology for like binoculars and telescopes, things of that nature. So we have a system of mirrors and lenses that cause total internal reflection. So total internal reflection is when the refracted angle is at least 90 degrees. Now the sine of 90 is 1. So if we go back to Snell's law, let's say we go all the way back, okay? If this was 90, right, this incident angle is our critical angle. So if you put 90 degrees in here, sine of 90 is 1. We've got n1 over n2 is sine of theta 1. You take the inverse sine of both sides, and you've got an expression for that incident angle. So that's what we did here, but now the indices are switched because it's just a notation thing, but we're going from n1 to n2, but n2 is less than n1. So we're going from a high index of refraction to a low index of refraction. So this is my expression. Again, it's a consequence of Snell's law. This is what we get when we set the refracted angle to 90 degrees. Sine of 90 is 1. If you solve for the incident angle, you get this expression. Okay, so that's my expression for the critical angle. This is the angle that we need to project the light in order for total internal reflection to occur. So that means no refraction whatsoever. All the light gets reflected back into the medium. Okay. So we'll do a couple examples of this. So a lot of questions deal with what's the necessary incident angle for total internal reflection to occur. If you know the index of refraction of the two media, you have this, right? Sometimes I like to play it safe and just go by Snell's law from the very beginning. Plug 90 in for the refracted angle, solve for the incident angle, just to make sure I get these two indices correct. Okay, just to make sure I get this ratio right. So sometimes you'll be asked for the critical angle, sometimes you'll be given the incident angle, and you'll have to find out whether total internal reflection occurs, in which case you have to find the critical angle and compare that to the incident angle. So that's what we're going to do in these next examples. So we've got a slab of fluorite with an index of refraction of 1.52. So the index of refraction of this slab is 1.52. It's surrounded by air. With an index of refraction of 1. So the first incident angle is 55 degrees. Now we know this reflected angle is 55 degrees. We'll have to do some geometry, or not use our knowledge of right triangles. We're going to find this new incident angle here. It's going to reflect again. And then we'll do it again, use this right triangle, use our properties of angles to find the new incident angle here. So the question says, which one of these points, A, B, and C, does light exit the slab? If light exits the slab, that means the incident angle is less than the critical angle. So we're going to have to solve for the critical angle here. All right, we solve for the critical angle here, and then we find the incident angle here, which we know, here and here. So if total internal reflection occurs, light does not exit the slab. But if total internal reflection does not occur, there's a portion of the beam that is refracted and will enter the air. So here is my drawing. I have the first incident angle, 55 degrees. And so I'll just go through the whole diagram and find my incident angles at points A, B, and C. So I've got 55 here. Law of reflection says this is 55. This is normal to this surface here. So 55's complement is 35 degrees. Okay. So I can do a couple different things. I can use alternate interior angles are congruent. I can say this is 55, therefore this is 55. Or I can say this is 35 and this is 35, right? This is a pair of alternate interior angles. This line right here is parallel to this line. Or I can take that 35 take its complement, because this is a right triangle right here, 35, I can call that 55. Take 55's complement and call that 35. So the incident angle at point B is 35 degrees. So I basically do the same process again. You kind of see a pattern here. We got 55, 35, 55, 35, and then we've got 35 is my reflected angle here. Again, I can do my alternate interior angles, 35 and 35, or 55 and 55, or I can use this right triangle again to say this is 55, here's 55's complement, here's 35's complement. So I've got an incident angle of 55 at point A, at point C, and then I've got an incident angle of 35 at point B. So I've got my indices of refraction. Fluorite is 1.52 and air is 1. So air is my n sub 2. It's less than n sub 1. Okay. If you get these switched around, odds are you're going to get a calc error. So I'm going to real quick, I'm going to take the inverse sine of the index of refraction for fluorite, 1.52, divided by air. And I get a domain error. Right? I can't take the inverse sine of anything greater than 1. So that's a good indicator that you got your indices of refraction backwards if you get an error when you calculate your critical angle. Okay. Again, you can always go from Snell's law, you can go from scratch. You can say fluorite sine of 55 equals air sine of something, or sine of 90, right? Plug 90 in for your refracted angle, and then you can derive this expression for the critical angle on your own. So air is less than fluorite, so it's going to go air over fluorite, N2 over N1. So we're looking for the critical angle, and then I'm comparing that critical angle to the incident angles at points A, B, and C. And so when I calculate the critical angle, I get 41.1 degrees. So any incident angle that's greater than 41.4 degrees will result in total internal reflection. If your incident angle is less than this, then we've got some refraction. So where does total internal reflection occur? Points A and C, because the incident angle at point A and the incident angle at point C are both 55 degrees, which is greater than 41.1 degrees. Where is the incident angle less than the critical angle? Right here at point B. 35 degrees is less than 41.1 degrees, so some light is going to refract, right? We still have a weak reflected ray inside the prism, but some light will escape at point B because the incident angle is less than the critical angle. Okay, so some light exits at point B only. So if the incident angle is less than the critical angle, you'll have refraction. If the incident angle is greater than the critical angle, total internal reflection occurs. We have another prism example. So this works kind of backwards, and we don't have a lot of information here. We have a light beam that enters a prism at an incident angle theta 1, which is what I'm being asked for. That's unfortunate. So we're going to have to kind of work backwards here. It strikes surface 2 down here at the critical angle. So we are given the critical angle. So here at surface 2, 42 degrees is the critical angle. That's also the incident angle of this ray. So we got total internal reflection here. We don't know if this is air out here. Doesn't say anything. And we don't know the index of refraction for the prism. So we're missing two indices of refraction. And we're also not being asked for the indices of refraction. I think it would be impossible to actually find an individual index of refraction for these two media. I think the only thing we could do is maybe find a ratio of indices of refraction. So here's my picture. I've got the critical angle is 42 degrees. That's also the incident angle here. Zoom in a little bit here for you. So I know this is 42 degrees. I'm going to kind of work backwards and hopefully get back to that incident angle, but I'm going to run into an issue here because I don't know the indices of refraction. I do know that this angle is also 60 degrees. So this is my incident angle at surface 2, also known as the critical angle, 42 degrees. Its complement is 48. So I can label this angle right here as 48 degrees. This is 60 degrees. The beam and these two surfaces make a triangle. Not a right triangle, not an isosceles triangle, but a triangle. So the sum of these interior angles have to equal 180. So you subtract 60 and 48 from 180 and you get 72. So that's good. I've got 72. That's not my refracted angle here at surface 1. 72's complement is the refracted angle. So I have to take 90 minus 72 to get that refracted angle. So that's 18 degrees. So I have this refracted angle. I know there's total internal reflection occurring right here. So I'm still stuck, right? I've got a refracted angle. I'm missing an incident angle, but I also don't have the indices of refraction. So I'm going to use Snell's law at surface 1. I'm just going to write it out. So I'm going to say n sub a is the index of refraction of the outside medium. N sub b is the index of refraction for the prism. So here's Snell's law. N sub a sine theta 1, that's what I'm looking for right here, equals n sub b sine theta sub r. So I have the refracted angle, 18 degrees, and I don't know n sub a, and I don't know n sub b. So I'm stuck, right? I've got one equation, two variables, so I'm in kind of a pinch here. Let's derive an expression for the incident angle. Divide both sides by n sub a, take the inverse sine of both sides, and I get theta 1 is the inverse sine of n sub b times the sine of the refracted angle, which I know, over n sub a. So I've got an expression, but I don't have the individual indices of refraction. But I do know the critical angle. Okay, I do know the critical angle. So the critical angle is the inverse sine of the index of refraction of the outer medium over the index of refraction of the inner medium. So it's n sub a over n sub b. Again, if you're a little hesitant to determine which index of refraction is the top or the bottom, go ahead and write out Snell's law like this and make your refracted angle 90 degrees, and then solve for that incident angle, and you'll get the appropriate expression for the critical angle, and you'll have your indices of refraction correct. Okay, so critical angle is the inverse sine of n sub a over n sub b. We don't know either of these. However, we know the critical angle. Right? The critical angle is 42 degrees. So I can at least use my critical angle formula to find a ratio of n sub a over n sub b. So that's what I'm going to do here. I'm going to take the sine of both sides, get rid of this inverse sine. So n sub a over n sub b is sine of the critical angle. So I plug 42 degrees in for my critical angle, and I get a value for the ratio of n sub a over n sub b, and that's 0.67. So I don't actually have to find out the individual indices of refraction here. All I need is their ratio. So n sub a over n sub b is 0.67, but I don't want n sub a over n sub b. The ratio here in my incident angle expression is n sub b over n sub a. So I have to take the reciprocal of 0.67, and I get 1.5. So I have a ratio of the indices of refraction that I need